Okay. I don't have time to go through the test today, so if you want to talk about the test, we just need to do it in office hours or something. We have to get through the rest of energy today. So here's what we have left in the semester. God, we're supposed to have a quiz today, and I made it, but I didn't print it. So free points, that doesn't sound so... Let's maybe, I'm thinking about what to do, but I'm not really thinking about that, no. That's, just write it on the board. I don't know what we're going to do about that. I'll get back to that later. We might have to do it next week instead. No? I wasn't the one, though. Okay, so here's what we have left. We have one more quiz. The lab tests are done now. Next week, so lab next week is the post-test of that diagnostic test, sort of the intuition test. So lab next week is the bubble sheet post-test. And and if you take this post-test, I'll give you 1 point back on an exam. Okay? And then exam 5, final. You have two choices for when to take this. You can take it on Monday with the night class. So that's 12/12 at 6 p.m. in S1326. Or the day class is scheduled for, not Tuesday, Thursday. $12:15 at 2 p.m. in this room, S1328. It's Thursday. Yeah, so you get, so I suppose, I mean, if your schedule's a little flexible, you can choose how much time you need to study for this, and, you know, one's at the beginning of the week, one's at the end of the week. Any questions about the end of the semester? All right. So last time, I introduced the work energy principle. And the work energy principle says, add up the work done by all the forces, and that's equal to the change in kinetic energy. And I talked about how to calculate work. So the work produced by a force is equal to the force dotted with the displacement vector. You can calculate that two ways. It's the x components multiplied together plus the y components multiplied together. Or you can also do it as the magnitudes of those two forces times the cosine of the angle between them. That angle has to be calculated with those vectors tail to tail. So this gives you a way you could, okay, so this way of calculating it requires constant force. So that's kind of an issue. But using the work energy principle, we could figure out how much things sped up or slowed down, at least due to forces that are constant over the motion of the object. But that's not how we're going to do it. We're actually going to use the work energy principle we're going to put it in a form called conservation of energy that is applicable just in certain cases. So we won't use this form of the work energy principle. And so we're going to deal with cases where we can sort of simplify the work energy principle, and that is dependent on this idea of conservative forces. So now we have to talk about conservative versus non-conservative forces. A conservative force is a force that only depends on the object's position. It doesn't even have to depend on the object's position, so I'll say at most. Depends on the object's position. So you can think of it like this. If you're given the object's position, is that enough to determine the force? Okay, so let's think about a few examples. First, ooh, look at this big weight here. How much is this weigh? 5 kilograms. Okay, so this 5 kilogram mass. If I tell you its position, is that enough for you to know the force that gravity is applying to it? No. It's not? It is. You know the mass. Actually, you know the mass, right? Yeah. You already know the mass. I told you it's 5 kilograms. Okay, yes, you know the mass. You know what object you're dealing with. And the question is its position enough to know the force? So weight is conservative because if I tell you where it is, you can figure out what the force is. In fact, that's more information than you need. You know, gravity applies a force of 5 times 9.81 down no matter where this is, right? So gravity is conservative. So weight is conservative. Because if you know the location, you know the weight force. And actually, the location, you don't even need that. Okay, so need. So now let's think about a normal force. So say we know the mass of this, too. Is it enough information, if I tell you that this is here on this table, is that enough information to know the normal force? This one's a little tricky, but is that enough? You might think so if it's just sitting there like that, but now imagine it's the same object in the same location, and we put something on top of it, apply a force down to it like this. The normal force changes, right? I'm increasing the normal force the more I push on this without changing the location. So that normal force isn't conservative. Saying that this object is here is not enough to specify what the normal force is. How about the friction force? Is it enough to know the location to know the friction force? No, because right now it's in this location and there's no friction force. If it's sliding this way, when it gets to that location, if I'm pushing it towards that wall, there's a friction force pushing that way. If I get to that location pushing it this way, there's a friction force that way. So the location of the object isn't enough to specify the friction force. So normal friction force are not conservative. And the thing that's useful about conservative forces is, so conservative forces are easy to deal with because they have what we're going to call potential energy. And the work done by a conservative force is equal to the negative change in potential energy. So if we can calculate the potential energy of a conservative force at one location and then calculate it at another location, and we subtract those two, that's an easier way of figuring out the work that's done by that force. Okay? So that's an easier way to calculate the work. In this class, we're only going to deal with two conservative forces. There are other ones, but these are the only two we're going to deal with. The first is the weight. And for the weight force, the potential energy, so I'll call it gravitational potential energy, is equal to the mass of the object times g, 9.81 meters per second squared, times the object's height. Okay, what is that height measured from? That matters, right? I mean, if this is how you calculate the potential energy, what's zero height? Is zero height sea level, or the ground, or the floor, or the center of the earth, It turns out that for any problem we do, you get to choose arbitrarily what you want to call zero height, as long as you're consistent through the whole problem. Okay, so for a problem, if you say you say the floor is what you're going to call zero height. You have to keep the floor your zero height through the whole calculation, but you'll get the same answer as if you, at the beginning, said that the center of the Earth was zero height. So we'll see that more.
Kind of like position 0 or
Yes, it is. You're right. Yep, you're right about that. So the weight is one of the conservative forces, and then the other one is spring forces, forces applied by springs. So what I mean, ooh, this is almost like a spring. So say that you have an object, you know the object, you know the spring, and you know where the spring is connected to. Okay? The spring pulls harder as that gets stretched out more. If you compress it, this isn't a very good example of this, but a metal spring, if you compress it, it actually starts to push on the thing. It wants to get back to its resting position, you know. And so no matter what happens before the instant you care about, if you specify the location of the object, figure out how long this spring is, how much it's stretched or compressed, that's enough to figure out how much force the spring's applying to the object.
So are you saying we're going to be given that every time? Or no?
I'm going to give you, just like I gave you the gravitational potential energy, I'm going to give you the spring potential energy now. So the spring potential energy is 1/2 kx squared, where x is the object's displacement from the spring's resting length. And what about this K? I haven't defined that yet. That K is what's known as the spring constant or the spring stiffness. A big value of K means the spring is stiff, it's hard to deform. And a low value of K means, you know, it's flimsy. It's easy to stretch, easy to compress. And the SI units for the spring stiffness are newtons per meter. Okay, so using this, you know, what's potential energy good for? What it's good for is the work energy principle relates kinetic energy of an object, basically its speed, to the work that's done. But calculating the work is hard. Calculating the work is easy if you have a potential energy. So using this idea that work is equal to negative change in potential energy, we can rewrite the work energy principle like this. The work done by all the non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. And it gets one step easier than that if there is no work done by non-conservative forces. So if there's no work done by non-conservative forces, this becomes conservation of energy. Which looks like this. The kinetic energy plus the potential energy at instant 1 is equal to the kinetic energy plus the potential energy at instant 2. This is the one that we're going to use. Okay, so how common is it that the only that something only has conservative forces acting on it? Well, if it's in free fall or it's subjected to the weight and the only other thing touching it is a spring, then you only have conservative forces acting on it. But often, I mean, the things that we're going to want to calculate are on the ground or rolling down a hill or something like that. And when something that's on the ground has a normal force acting on it, and that's a non-conservative force. So how useful is this equation? What was that? Well, so actually that is an example that we'll do, but it turns out that a lot of cases will meet this requirement, and I'll talk about why. So how likely is it that no work is done by non-conservative forces? Well, remember when I was talking about what work is yesterday, I said that if the force direction is perpendicular to the direction of motion, well, did I say that? What I said was this. The work was equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. And so if the force and the direction of motion are perpendicular to each other, you have cosine of 90 degrees. What's that equal to? 0. So which is 0 when theta is equal to 90 degrees. So if a non-conservative force is perpendicular to the direction of motion at every instant, that force does zero work. And there are two examples where this is going to come up all the time in our problems. So two important examples. The first one, I'm going to show why normal forces never do any work. So even though normal forces, they're non-zero forces, they're non-conservative, so they don't have potential energy, we don't have to worry about them because they never do any work. So normal forces in rolling and sliding problems that never does work. So, okay, think about an object rolling on an incline. The direction of motion is up or down the incline, right, parallel to this surface. What's the direction of the normal force? Yeah, the normal force is that way. And so the direction of motion and the normal force are always perpendicular. So now what that says is that in rolling or sliding problems, say that you have a problem where something's rolling down a hill, okay? The forces acting on the thing are the weight force, which is conservative, the normal force, which is non-conservative, but it doesn't do any work, and so we can use this simple conservation of energy form, okay? Any questions about that? Anyone? I always look at Tatiana because she always knows what I'm talking about. Not like the rest of you idiots. Talk to Tatiana if you have any questions. Okay, and then there's one more example that's going to come up all the time. If you have a centripetal force during a circular motion, that's also non-conservative, but it does zero work. And so a centripetal force is a force that points towards the center of the circle. Okay? So if there's the circular path, there's the object. At this instant, the direction of motion is like that. A centripetal force is like this. Those are perpendicular, and so the work is equal to zero. Yeah, let me, direction of motion is perpendicular to a centripetal force. How far you want it up here?
Oh, just like number, I just wanted to see what number 2 said.
Okay. All right, so we can use conservation of energy in any problems that have combinations of these four things, basically. Centripetal forces in circular motion, normal forces, spring forces, and gravitational forces. Okay? The two conservative forces are springs and gravity. And the two non-conservative forces that don't do any work are normal forces and centripetal forces. Okay? And so you'll see that every energy problem we do is going to be a combination of those four things. All right, so let's just do a few examples. So the first one, let's say that there's a skier up on top of this hill. Yeah. This is Minnesota skiing, so you can make it intense like this, but you can't make it very tall. So the height is 40 meters. And the question is, if there's no friction, how fast is the skier going when he gets to the bottom of the hill? This is, I was never a skier or anything, but I was really disappointed when I found out that like Olympic downhill ski racing isn't just seeing how fast you can get to the bottom, you know? Like they still make you turn and stuff. That's lame. Okay, so no friction. So in a way, this isn't a, how often do people ski like that? Well, the one time I went skiing, I did do it like that accidentally, but mostly you're like, and all the times you're doing that, oh, this powder is awesome, man. Every time you do that, that's friction, you know? You're turning like that to create friction. So this is just someone just putting their head down and just oh yeah, like this is like the ski jump. I'm going to do that problem like that next time. It's the ski jump, and then we could calculate how fast he's going when he takes off the jump. Yeah. I should find out how high that is. It's probably not 40 meters. 40 meters is pretty high.
It looks really scary, though.
It does look really scary. It looks like they just built a smaller one next to it. Okay, so you could do a problem like this using Newton's laws, but it would be way harder to do than it is using energy. First, you'd have to figure out the exact shape of the hill and represent it mathematically, which, you know, the way I drew it, that would be really tedious, obviously. And then second, you have to use calculus. You'd have to come up with this expression you'd have to use Newton's laws to come up with the acceleration. And then you'd have to use calculus to get from the acceleration to the velocity. And obviously, we haven't done that in this class anyways. It is possible to do it. It's just a lot harder. But we're going to see that it's pretty straightforward to do this using energy. Okay, so first we have to think about what forces are applied to the skier. So let's think about a free body diagram at just some arbitrary moment. So there's the skier, his hat. Okay, there's the skier. So What forces are acting?
Natural force.
Yeah, normal force. And then the weight. Okay, so these are the only two forces. Let's think about what's conservative, what's non-conservative. Okay, so are either of these conservative? Conservative are the good ones. Non-conservative are the bad ones. Yeah, gravity, the weight is conservative. So that's easy to deal with. What about the normal force?
It doesn't matter.
That's right, it won't matter. That is non-conservative, which is a concern, but it's not going to do any work. So the normal force is non-conservative, but it doesn't do work. So we can use conservation of energy. So the way I'm going to set up this problem is I'm going to, conservation of energy always deals with two different instants. And if you add up the potential and the kinetic energy at each instant, they have to add up to the same thing. So I'm going to make a column for when the skier's at the top of the hill. And a column for when the skier's at the bottom of the hill. And at each of these, I'm going to calculate the kinetic energy. And I'm going to calculate the gravitational potential energy. And then we're going to put it into the conservation of energy equation. Okay, at the top of the hill, kinetic energy is 1/2 times the skier's mass times the speed squared. Do we know the skier's speed at the top of the hill? Well, I didn't really say it, but in my head, he was at rest, so speed is 0. So 0 kinetic energy at the top of the hill. And now the gravitational potential energy. That's equal to mgh. So we have the skier's mass times 9.81 times the height. So now this is where that issue comes up of what are we calling the 0 height. Once in this problem, we get to choose what we want to call the 0 height, and then we have to keep it consistent for the whole problem. So let's call 0 height the bottom of the hill. Okay? So if 0 height is the bottom of the hill, what's the skier's height at the top of the hill? 40, yep. To know what the 0 height is? No, I can tell from the numbers you use. Yes?
Why is it not negative 9.81?
That constant g is always positive 9.81, and then the negatives just come from the direction. So what do you get here? 392.4m.
Wait, I'm sorry. So are we using the mass times gravity times height right now?
Yes,
Okay.
that's right. Okay, so now at the bottom of the hill, kinetic energy is 1/2 times the mass. Do we know his speed at the bottom of the hill? That's what we're trying to find. It's not. So we're doing this. So you might think at the bottom of the hill you stop or something, but this this only deals with, once he stops, he's stopping because of some other thing that's happening that's not represented here, running into a wall or a person or something. And so we can only figure out the speed before that other thing intervenes, okay? So we're just trying to figure out, like, as he goes down the hill, he goes faster and faster. Once he's gone down 40 meters, how fast is he going? And so that's what we're trying to find. So I'm just going to leave this as V, and we're going to solve for that V. And the gravitational potential energy is mass times 9.81 times 0, because that's what we chose as our 0 height, the bottom of the hill. And so gravitational potential energy is equal to 0 at the bottom of the hill. And now conservation of energy says add up all this stuff at the top of the hill. That has to be equal to all the stuff added together at the bottom of the hill. So 0 plus 392.4 m is equal to 1/2 mv squared plus 0. So 392.4 m is equal to 1/2 mv squared. You can divide both sides by m, get rid of those. And so now you have 392.4 equals 1/2 v squared. What that says that we get an equation where m cancels out is that the speed of the skier, if there's no friction, doesn't have any dependence on the weight. So a bigger person doesn't go any faster. 784.8 is equal to v squared. Take the square root of both sides, and you get that v is equal to plus or minus 28.1 meters per second. And do we want the positive or the negative? This is a speed, not a velocity, and so we just always take the positive. So, yeah, remember that energy doesn't ever give you directional information. So that's why, velocity is a directional variable. Speed doesn't have direction, so we're using speed. Okay, yes?
I'm sorry, can you just go over, I'm a little bit confused. I understand what you did for the, what does COE stand for again?
Conservation of energy.
I understand how you got that, but I'm a little bit confused about how you got the equations for the top of the hill and the bottom of the hill.
Yeah. Okay, so kinetic energy is always equal to 1/2 times the mass times the speed squared. And gravitational potential energy is always equal to mgh. And so all I did was plug in the information that we know at the different instants to those expressions.
Okay.
So like at the top of the hill, we knew the speed was 0, so we got 0 for kinetic energy. The height at the top of the hill, once we chose our 0 height to be the ground, the height was 40, and so we could calculate that the potential energy was this.
Okay, I think I was just confused because I thought you were doing a different thing for each side, but now I'm realizing that it's 0 because the speed at the top was 0.
Right, yes. So it's the same expressions in both, but you're just changing the height and changing the speed.
Okay, that would never happen where you would do two different systems.
Nope,
Okay,
nope, it'll never happen.
thank you.
Oh, really? Yeah, right. 0, 1. Thank you. Some student probably told me that before. Okay, so 60 miles an hour. So if you go to 40 meters down a hill with no air resistance and no friction, that's how fast you'd be going at the bottom, 60 miles an hour. So be careful. Yes?
Okay, this might be stupid, but if you gave us this question, how would I know that I'm not just solving for VF? Like that I wasn't using
Yeah.
kinematics?
Kinematics. So the only kinematics that we did this kind of stuff for was, well, how would you know it's not kinematics? If you tried to use the kinematics equations, first of all, you would see that you don't have enough information to solve it. Because you would if it was a free fall problem. But this isn't free fall because there's the normal force acting too. And then also, I think I tried to get at this last class. You want to get to a point where it sort of triggers you when you see a problem that's relating a change in position to a change in speed. If a problem says when the thing goes from here to here, what's the change in speed, or what's the speed at the end, or what was the speed at the beginning? Those are exactly the things that conservation of energy makes easy. So that's what, when you see this problem, that's what would ideally be the first thing. You'd say, okay, we're dealing with a change in location and a change in speed. I want to think conservation of energy. But if you didn't think that and you started trying to work through kinematics equations, which wouldn't be totally unreasonable, you would just see you don't have enough information. Any other questions about that? Okay, let's do another one. So let's say we have a spring. And let's say the constant is 500 newtons per meter. And a mass of 10 kilograms. And let's say we fire a bullet into this. So like this is a wooden block. We fire a bullet into it. What's a mass of a bullet? Is 10 grams a possible mass of a bullet? Or is that too little or too big? Okay. So that's 0.01 kilograms. And what's a speed, in miles per hour, how fast does a bullet go when you shoot it out of a, okay, 7. So let's say 1,000 because the numbers are easy. Oh, well, 1,000, let's say 500 meters per second then. 400. Okay, so what's going to happen is the bullet's going to stick into the wooden block, and then the two of those things together are going to compress the spring. Okay? And so what we want to calculate is how much will the spring compress before it, so this is going to hit, it's going to compress, and then it's going to oscillate back and forth. How much will the spring compress before it goes back the other way?
So right now it's at rest in some way,
Yes, yes. Okay, so this problem combines conservation of linear momentum, because there's a collision, and conservation of energy, which is the part where the bullet and the mass together compress the spring. Okay, so we're going to do it in two parts. Conservation of linear momentum for the collision, and conservation of energy for the compression of the spring. So let's take a top view for the, we're going to start with the conservation of linear momentum. We have the block sitting here at rest. If it's at rest, the net force on the block has to be equal to 0. And we have the bullet going this way, 400 meters per second. There is gravity on the bullet, there is weight, but that's acting into the page, so from the top view that doesn't show up in our calculation. And so conservation of linear momentum says add up the momentums before the collision. So that's 0.01 times the velocity vector, 400, 0. Plus the mass of the block times its velocity before the collision. This is an inelastic collision, which means after the collision, these two things act as if they're a single object. So now we have a combined mass of 10.01, and we're trying to calculate the velocity after the collision. So the x equation says 4 is equal to 10.01 Vx. The y equation says 0 is equal to 10.01 Vy. So for Vx, what's 4 divided by 10.01? 0.3999 or something. 2 nines. And Vy is equal to 0. Okay, so after the collision, V is equal to 0.39960. That's the velocity after the collision. And now we're going to do conservation of energy. So let's think about just an arbitrary free body diagram. What are the forces acting on the block bullet system? There's a weight. There's a normal force. And then there's a spring force pushing this way.
So why is the force of the spring pushing into it? Would it not be pulling it towards the wall or no?
Yeah, that's a good question. So if the spring always wants to get back to its resting length.
Yeah.
So if you compress the spring, it tries to push you back.
Oh, okay. I
You know,
thought
if
it
you
was
push on the
down.
spring, it tries to push back. If you pull on it, it tries to pull back.
Okay.
But for this way of thinking about it, that's not, you don't even have to make that determination. The energy will come out, you know, it'll give you that answer on its own. Okay, so what are the conservative forces? And what are the non-conservative forces? What are the conservative ones? Yep. Yep, and spring. And then non-conservative? Normal. Right, doesn't do any work. So now we can think about our two instants are the start of the compression and the end of the compression. We're going to figure out the potential energy due to gravity, potential energy due to the spring, and the kinetic energy at both of these two instants, and add them all up. Okay, so potential energy due to gravity. What do you want to choose as our zero height? Yeah, it might as well just be the height that it's at. The thing stays at the same height the whole time. So if we choose our zero height to be where it is, then the gravitational potential energy just goes away. So
So you're saying it's going to be the height of the bullet?
the height of the whole system. Like once that bullet lodges in there, once the bullet lodges in here, the system stays at the same height the whole time it rolls. Okay. So we're just going to say that it's at zero height, and then it's going to fade away. So this is equal to 10.01 times 9.81 times 0, so 0 gravitational potential energy. Then we have the spring potential energy. That's equal to 1/2 times, what did I say, 500 was the constant? The spring constant is 500. And then at the start of the compression, how much is the spring compressed? Like right after the collision ends, the bullet's in there, how much is the spring compressed? Nothing. It hasn't moved at all yet. And so that's just going to be 0 squared. So there's no spring potential energy. And then the kinetic energy is equal to 1/2 times the mass, 10.01, times the speed squared. What's the speed at the start of the compression? So this is, now the compression is after the collision ends, so the speed at the start of the compression is the one that we just calculated. That's the 0.3996. Can someone calculate that number? .8? Yes. Okay, And then at the end of the compression, what's the height of the system? It hasn't changed, so it's still 0. What's the compression of the spring? We don't know. That's what you were suggesting before, so I'm just going to leave this as x squared, and we're going to calculate that x. And then when it's all the way compressed as far as it can go before it starts to go back in the other direction, what's its speed? 0. Yep, exactly. So the kinetic energy is 1/2 times 10.01 times 0 squared. And now conservation of energy says 0 plus 0 plus 0.8 is equal to, oh, this was 0, is equal to 250 x squared. So x squared is equal to 0.8 divided by 250. What's that? Some 0.0032. And then what's the square root of that? The square root of 0.0032? 0.056 meters. And so this is, I'll take the positive. So it's compressed 0.056 meters, which is 5.6 centimeters. Not really in this case, since we're just interpreting that number to be how far the spring is compressed. Any questions about that? So this is sort of this is actually in the ballpark of the way that people used to measure the muzzle velocities of guns before there was high-speed video or like laser timers, that kind of stuff. Like, how would you measure something really, really fast before you had these high-tech things? Well, the way they did it is we started this problem by knowing the speed and measuring how far the block would move. But what you can do is shoot the bullet into the block, measure how far it moves, use those same equations to back calculate the speed, and then it's a way to get a good estimate of the speed of the gun without being able to visualize it. Did someone have a question? Yeah. Yeah, there really isn't except for office hours. I have, and that brings up one point. I'm going to do my usual office hours during finals week. So next Monday and the Monday after, I have office hours in the lab from 3 to 6, and there'll be lots of people in there working on problems, and I can answer questions. So that's, sort of that idea. So yeah, if you can make it 3 to 6 or any time in there, either of the next 2 Mondays, that's a good one. Yep. Yeah, the practice problems. That's right. And there's one other thing I wanted to say about the practice problems. In the practice problems, in conservation of linear momentum, there are elastic collision problems. So ignore any conservation of linear momentum problems that mention elastic, or bounce apart. Okay, the only ones we're doing are the ones where the things stick together. I'll either today or tomorrow I'll look through them and tell you exactly on D2L which parts of which problems you can skip. But we just skipped all those elastic calculations. All right.